The second law of thermodynamics, entropy, microstates, and the Boltzmann equation. Okay, so let's continue our discussion of the second law of thermodynamics. We said in the previous discussion that the total entropy change for any spontaneous process is positive. In other words, entropy increases for a spontaneous process. Now, what we didn't say is that this increase in entropy actually involves an evolution from less probable configurations to more probable configurations. And this has to do with the microstates in the system. As the number of microstates increases, then the entropy increases. Now, a microstate is an instantaneous property of the system. If we have gas in a container, for instance, then microstates could include the instantaneous velocities of the gas molecules. It might be their positions in the container. And remember, we could also be talking about atoms, ions, and in general, we just call them particles. Now, we can increase the number of microstates for a system in a couple of ways. One is by increasing the volume, and the other is increasing the temperature. And in this video, we're going to talk about the volume more, but we'll talk about the temperature later on. There are a lot of complicated factors involved in temperature and entropy, so we will discuss it, but we're not going to go greatly into depth. Now, let's do an example of counting microstates. And so we're going to have a scenario where we have 4 distinguishable particles in one side of a 2-compartment container. So what that means is that we have 4 particles and we can tell them apart. Now, we're going to figure out how many possible ways there are to distribute these guys between the 2 sides of the container. Okay, so here are the microstates that come out of this problem, but let's start talking about it. So here's our 2-compartment container here. And notice that we have 4 particles on one side, yellow, blue, red, and purple. Now, we're going to open this stopcock, and we're going to allow particles to go into the other bulb. So if we allow only one particle to come over here, then let's say we want to allow the purple one, then we have another microstate. Let's say we want the red one over here, but we still have 3 in this side. That's another microstate. Here's another microstate with the yellow and then finally the blue. Now, this is a category of arrangements, of course. So where we have 3 particles on the left side and 1 particle on the right side. Now, we can also count up the microstates for doing the opposite. So let's say that we keep 3 particles in this side, in the right side, and only let 1 go to the left side. So we'd have 4 more microstates with this category of arrangement. What about allowing them to split equally, 2 and 2? So in this one, let's go ahead and keep yellow and blue over here, put red and purple here, change places, and we have another microstate. Now let's exchange partners. So now purple can be with yellow and red can be with blue. And then again, let's just swap them. And then finally switch the partners one more time. So we have yellow with red this time, blue with purple, and then again just swap the bulbs and we have another microstate. So here is the most probable. This is most likely that the particles will end up in a configuration in this category 3, okay? And then finally, our last microstate that I didn't mention yet is taking all 4 particles, taking them from the left bulb and just putting them in the right bulb, and now leaving the left bulb empty. So you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different ways to arrange the 4 particles that you can tell apart, and each one of those is a particular microstate. Now, Boltzmann worked with entropy and developed an equation that relates the microscopic microstates to the macroscopic thermodynamic state. And the relationship between the number of microstates and the entropy is given by this equation. So here we have entropy S, and that's equal to the Boltzmann constant, which is 1.38 times 10 to the negative 3 joules per Kelvin. And we're going to multiply that by the natural log of the number of microstates. And that gives us the entropy for that system. Now, what if we have a process? So what about evolving from a less probable to more probable configuration? What could we do? Well, we would calculate delta S in this case. We'd still have the Boltzmann constant, and it would be multiplied by the natural log of the final number of microstates divided by the initial number of microstates. So let's go ahead and do a calculation where we figure out the number of microstates without swapping them manually, so moving them manually into two sides of the container. So we're going to start again with the same 4 distinguishable particles, and they're going to initially be sealed in the right side of a 2-compartment container. Now, we're going to open the stopcock and allow the particles to distribute throughout both compartments. So how many possible arrangements are there initially and finally? And then we're going to calculate delta S for this process. So how many microstates did we start off with? So remember our discussion earlier where we had 4 particles in one side and none in the other. And so in this case we were told they start off in the right hand side. So there's only one way to do that, right? So 4 over here, 0 here. So that means there is 1 microstate associated with this initial state. Now, what about in the final state? Now think about what happened to the volume. So we started with, I'm going to flip back here. We started with all the particles in this volume. But now we're basically doubling the volume and allowing them to come over here too. So the way that we can calculate this is take what we did to the volume and raise it to the power of the number of particles that we are working with. That's the number of particles. And that's going to give us the final number of microstates. So doubling the volume to the 4th power, because we have 4 particles, is going to give us 16 different microstates. So there are 16 possible arrangements of those 4 particles that we can distinguish when we double the volume. How do we calculate delta S? This is actually not too bad once you have the number of microstates. So you just take your Boltzmann constant and multiply it by the natural log of 16 divided by 1, which of course is just 16. And you're going to end up with 3.83 times 10 to the negative 23 joules. So basically the entropy increased, and we know it increased because the sign is positive. It increased 3.83 times 10 to the negative 23 joules when we doubled the volume. So next we're going to talk about predicting entropy changes qualitatively, and we're going to do some examples to go along with that.